In this tutorial, we're going to learn how to run a DC simulation to test the capacity for power of a cascode transistor configuration. If you have access to my ECE 5321 class folder, you can go there now and open up the cascode transistor DC schematic. The schematic is shown here. We've connected two transistors in a cascode configuration and added 3 voltage sources and a substrate contact. One voltage source we've added a DC variable called VGS and connected to the gate of the first transistor. The second voltage source we've given a constant voltage of 1.8 volts and connected that to the gate of the second transistor. Finally, we've added a third DC voltage source with a DC variable of VDS and connected that to the drain of the top transistor. Now we're going to open up the analog design environment. If you have access to my ECE 5321 folder, you can also open up the artist state associated with this schematic. With the artist state open, we'll look at a few setup things that we will need to account for. So the first thing that we'll look at is model libraries. We need to set up model libraries so that our model libraries point to the appropriate path for design wafer and all models.scs, and make sure that all models.scs also points to section TT. We also need to import any variables from the schematic. So we can go to variables, copy from cell view, and we will have variables VDS and VGS. We'll set these both at their maximum value of 1.8 volts for this process. Finally, we go to Setup Simulation Files, and notice that I've also enabled a stimulus file called mosdc.scs, which is available under my 7RF folder. We can look to see what's in that file, and it's just 2 lines that save the operating point for both transistors. We're going to do a DC analysis, so we can open up Analyses, choose, and select DC. Make sure that Save DC Operating Point is selected, and also in the sweep variable, design variable VDS is selected. We're going to sweep VDS between 50 millivolts and 1.8 volts with a step size of 50 millivolts. Let's also look in the Options tab and make sure that the Cap Tab Parameters Cap Tab box is selected. I've added a couple of outputs by going to Outputs to be saved, select on Schematic, and selected the drain of transistor TN1 and the minus terminal of the voltage source that has the variable VDS set. I've also added a couple of output equations to estimate what the knee voltage is, that is the saturation voltage for both transistors. The saturation voltage is the minimum voltage where both transistors are saturated, or VDSat TN0 plus VDSat TN1. The expression to find that is shown in this calculator. As PV TN0 VDSat result DCOP plus so on and so forth. Now I've also added an equation to estimate what the drain current is at the edge of saturation, and this is what such an expression looks like. Again, this is available in my artist state. If we were trying to find a family of characteristic curves for the transistor, we would do a parametric analysis by going to Tools, Parametric Analysis, and setting a variable VGS and sweeping it across a range from approximately 0 up to VDD for the process in linear steps totaling 10 steps. If we were interested in finding these curves, we could run this simulation by clicking on Run Selected Sweeps. In our case, we're only interested in finding the characteristics for maximum output power, which corresponds to maximum VGS of 1.8 volts. So we're just going to run the simulation sweeping VDS and leaving VGS set at 1.8 volts. Note that upon completion of the simulation, a plot of the drain current with respect to the drain to source voltage shows up. Here we see a couple of distinct regions of operation, triode linear region, and then as the drain to source voltage increases, the device goes into saturation. But it's difficult to tell where the device goes into saturation due to relatively indefined point of inflection. We know when it goes into saturation is when both devices reach VD sat, or where the knee voltage is of 597.1 millivolts. At 597.1 millivolts, we can see that the current is approximately 500.1 milliamps, which is the same as our max current equation yields. We can also find a couple of interesting things about the device capacitance by going to Results, Print, DC Operating Points, and selecting one of the devices. When we do this, we get all of the internal device capacitance. These capacitances are calculated by taking the charge derivative with respect to voltage across the terminal. For instance, CdB is the charge derivative with respect to voltage across the drain to bulk terminal. Negative signs don't matter, it just means that the slope of the derivative was negative. But this can be kind of confusing when we're trying to estimate the total capacitance for the device. We'll look at a different means to estimate capacitance in a moment. From this operating point, we can also find interesting things such as the transistor's transconductance, its output conductance, its threshold voltage, on resistance, etc. We can also go to Results, Print, Capacitance table, and the capacitance table will give us an estimate of the total capacitance at any terminal of the transistor. For instance, at the source terminal of transistor TN1, we have a total capacitance of approximately 2 picofarads. Something that's misleading about these capacitances is that these are small signal capacitances. They don't reflect any change in DC bias point. If you were to change the DC bias point, as a matter of fact, you'd see very different capacitances as the operation region of the transistor changed. In the next video, we'll look at using periodic S parameters to estimate capacitance for large signal variation.